Chapter 19.5 Salts and Solutions. Let's look at titration of a weak acid strong base and a strong base strong acid. So here we have the pH on the left, and we are adding a 0.1 molar solution of sodium hydroxide in milliliters. The weak acid strong base is the green line. When we start here at about 3, the strong acid strong base is the orange line, and we start at a pH of 1. So you can see at this point, follow the yellow line or the orange line up. The equivalent point, that is where the point in a titration where the number of moles of hydrogen ions equals the number of moles of hydroxide ions. That's an equal relationship, and you can see here with a strong acid strong base we have a pH of 7. But at a weak acid and a strong base, we get at the equivalence point where the moles of hydroxide and hydrogen ions, they'll equal each other at a higher pH. That's about 8.7 or so. Now why is that? Why is the same amount of base and acid used in each titration? It's because the number of equivalents of acid and base are equal here. And that's because the ethanoic acid here, it will react with water to produce hydroxide ions, as we can see here. This is a weak acid. It reacts again with water and it produces hydroxide ions. Hydroxide ions will push the value of the pH up, whereas with the chlorine ions, they will not react with water, and they won't produce H3O plus or OH minus. But if a weak acid or weak base is in solution, the salt could react with the water and produce hydroxide ions or protons, thus making the pH lower or higher. Now if you remember, a salt consists of an anion from an acid and a cation from a base. It forms from the neutralization reaction, such as NaCl. So if we had HCl plus NaOH, you get NaCl plus water. Now this is the salt. It's the anion from the acid and the cation from the base. Salt hydrolysis is the process in which cations or anions of dissociated salts accept hydrogen ions from water or donate hydrogen ions to water. So that means if it accepts hydrogen ions from the water, there'll be OH minuses in the water now, in the liquid. If they donate hydrogen ions to the water, it'll be an H3O plus hydronium ion. So in general, salts that produce acidic solutions contain positive ions that release protons into the water, and salts that produce basic solutions contain negative ions that attract protons from the water. So you will get the water to produce hydroxide ions. So with weak acids and weak bases, you have these salts, and they're inside a little acidic solution or a little basic solution. Let's look back on this titration of a weak acid and a strong base. This CH3COOH is ethanoic acid. We add it to the strong acid, or excuse me, the strong base, and we get sodium ethanoate. This sodium ethanoate right here is the salt. So we had a weak acid, a strong base, and we get the salt here plus water. But it's not done there. Some more stuff happens. The sodium ethanoate will break down into the ethanoate ion and sodium. And if we have charge there, we can react. That charged ethanoate ion will react with water. We have a negative there, so what that's going to do, we have a little bit going here, heavily favored in the reactants. It's going to react with the water, and we're going to produce back to ethanoic acid and hydroxide ion. And it's the presence of those hydroxide ions right here, that causes the pH to be up here and the equivalent point to be higher, because we're going to have that much. We need 50 mils of that strong acid in order to make an equivalence point of the same number of moles of hydroxide with the same number of moles of hydrogen. So here we can see the basic pH of some salt solutions. We have some universal indicator which will show the pH. This one, beaker A, is ammonium chloride. The pH is about 5.3. So that means at the equivalent point it started to add, it's added and reacted, the salt reacted with water to produce protons. Sodium chloride, this was produced, it was a salt of a neutral solution of a strong acid and a strong base. We have a pH of 7, so there was no extra protons or hydroxide ions. And this is the sodium ethanoate that we just talked about. It has a pH of 8.7 at the equivalent point. So this was reacting with water to produce more hydroxide ion. This was reacting with water to produce more proton. And thus, this at the equivalence point raised the pH. This at the equivalent point lowered the pH. So it makes sense that a strong acid and a strong base would be neutral. Strong acid, weak base would be acidic. And a weak acid and a strong base would be basic. Just basically common sense. Let's look at buffers. Buffers are extremely important to life. They're not just something you do in the chemistry lab. A buffer is a solution that resists changes in pH, so it stays basically constant when small amounts of acid or bases are added. So we can keep adding acid to a base with a buffer and it will stay about constant, and vice versa. If we add base to an acid, it will stay constant as well. A buffer is a solution of weak acid as one of its salts, or a solution in one of its salts. So buffers are really just weak acids and salts, or weak bases and salts. Right, an example of a buffered system. Here we have two bases. The pH is about 8 on both of them. They're identical. And so we're going to add some acid and see what happens to the buffered solution and the unbuffered solution. So in the buffered solution, we added some acid and the pH basically stays the same. It resisted the changes to the pH. But when we added acid to the unbuffered, it just quickly changed, and now this pH is about 3. So the buffer basically protects the system from pH changes. Example is in your bloodstream. So buffer example, your blood has a pH of about 7.4. And you have buffers in your blood, in your cell, to keep it around that level. So you know you eat a lot of acidic things. You might have some basic things in your diet. Mostly you eat different acids. And even the process of breathing out creates acidic situations in your blood. But the problem is you can only survive within this very small range of a pH of about 6.8 to 7.8. That's not a lot of room to screw around with. And with all the things in our body and around the air and the environment, our blood can really change very quickly if we didn't have these buffers in our system. Cells also have buffers. Other cells of our body have buffers that will resist the change to pH, and this is all to protect us. So we have these very weak acids and salts, or weak bases and salts, to help stop pH from either going too high or too low.